Assalamu alaikum beautiful people, welcome to the class of chemistry. This is Shehrbana and I'm gonna make you learn the lesson in the most easiest possible way. If you like the video, please subscribe to my YouTube channel and do not forget to press the bell icon. So let's begin.
Alright students, so today in this video we are going to complete our chapter by discussing its exercise short questions and by solving its exercise numericals, and our chapter named Chemical Equilibrium will be finished. In this video, we are going to discuss the 14 exercise short questions given in your book, and you will have 4 numericals which definitely I'll solve for you guys. So moving ahead towards the short questions, let's see our first question, that what are the irreversible reactions, and give a few characteristics of them. So we all know that irreversible reactions, in irreversible reactions, the products do not recombine to form the reactants. In these type of reactions, the reactants, the products do not recombine to form the reactants. You can see the example, hydrogen combined with oxygen to give water molecule. This is a type of irreversible reaction. If we see the characteristics, these are quite simple. You guys already have studied in the chapter that these are represented by a single arrowhead between the reactants and products. These reactions are proceeded to completion. It means that in these type of reaction you will always get the final product. Like in this reaction, you can see that by the combination of hydrogen and oxygen you finally get water, which do not decompose into oxygen and hydrogen, because the arrowhead shows that the reaction is irreversible. Next is these reactions may be converted into open or closed vessel. It means that the condition for this system is not mandatory here, as we have studied in reversible reactions that these can only be taking place in the closed vessels. But in the irreversible reaction, they can take place in any sort of system. Either it is closed, either it is open, either it is isolated. We have explained these 3 type of systems in the previous lectures. You can check the videos from the playlist. Last but not the least, there is no sign of equilibrium state in these reactions. These reactions do not have any sort of equilibrium. So moving ahead towards question number 2, that define the chemical equilibrium state. Here you just need to define it, so which is very simple. We know that in a chemical equilibrium, the rate of forward reaction is equals to the rate of reverse reaction. So here you can see that when the rate of forward reaction takes place at the rate of reverse reaction, the composition of the reaction mixture remains constant. It is known as equilibrium state. For example, here you can see a reversible reaction where nitrogen and hydrogen combines together to form ammonia, and in return ammonia decomposes into hydrogen and nitrogen, because this reaction is reversible reaction, and the equilibrium constant value for this reaction is 2.86. This is the unit for Kc for this reaction. Okay, question number 3, give the characteristics of reversible reaction. Now we are going to discuss the characteristics of reversible reaction. So these are represented by this arrow, double-headed arrow between the reactants and products. It can be attainable from either way, like equilibrium can be attained either from the reactants or from the products. It is not, a reversible reaction never goes to completion. Here in these type of reactions you will never ever get a final product, because they never goes to completion. And a very important condition, that it always carried out in a closed vessel, or you can say in a closed system, where heat can be get out of the system, but the matter could not be able to get out of the system. So this is known as a closed system, or you can say the reaction taking place in a closed vessel. In these reactions, the equilibrium state is an ultimate goal. In the reversible reaction, there should be an equilibrium. It means that the rate of forward reaction should be equals to the rate of reverse reaction. Okay, so moving ahead towards question number 4, how is dynamic equilibrium established? First of all, we need to know that what does dynamic mean? Dynamic means to move. anything which is moving, this is known as dynamic. So you can see that when the reactions does not stop, only the rate of forward and reverse reactions become equal to each other but takes place in opposite direction. It means that when the reactants are converted into products, at the same time the products are converted back into the reactions. So both the things are moving. Reactants are converted into products are converted into reactants. So the rate becomes equal, but both the reactions takes place in opposite direction. Once the dynamic equilibrium is established, it just keep on going until the conditions are changed. I am repeating the example of ammonia so that you guys never get confused. There are so many other examples, but just for the sake of convenience, I am using the same example in wherever it is needed. Okay, so question number 5, why at equilibrium state reaction does not stop? At equilibrium state, the rate of forward and reverse reaction becomes equal to each other but takes place in opposite direction. This question is exactly the same. We have studied the question number 4. Products recombine to form the reactants, because in equilibrium, or you can say that in dynamic equilibrium, things are happening. Reactants are converted into products and products are converted into reactants. Things are happening at the same rate. The rate equifies, but they are taking place in opposite direction. Again, the example is the production of ammonia and the decomposition of ammonia into hydrogen and nitrogen. Alright, so moving ahead towards question number 6, that why is equilibrium state attainable from either way? An equilibrium state is attainable in either way because it may start from reactants to give products, while the products recombine to give the reactants. As we have studied before, that it is not mandatory in reversible reactions that equilibrium is established. It's supposed to be established from the reactants, or it is supposed to be established from the products. These things vary reaction to reaction. It depends upon the type of reaction. It depends upon the need of reaction. So we never know equilibrium can be attained from either way, either from products or from reactants. So here you can see that the reactants are converted into products and products are converted back into the reactants. Okay, so question number 7 is, what is the relationship between active mass and the rate of reaction? So first of all, we need to know that law of mass action describes the relationship. This is the basic answer, that law of mass action describes the relationship between active masses of the reactants and the rate of the reactions. Okay, so according to this law, the rate at which the substance reacts is directly proportional to its active mass, and the rate of a reaction is directly proportional to the active masses of the reacting substances. We have explained this law in detail in the previous lectures. You can see an example. A and B are the reactants which are converted into products C and D, and this is a reversible reaction. It means that AB is converted into CD, but at the same time CD is converted back into AB. So at equilibrium state, the rate of forward reaction would be equal to the rate of reverse reaction. So to cut short directly from the lecture, we will get Kf, which is the equilibrium constant for forward reaction, multiplies by concentration of A multiplied by concentration of B, which is equals to Kr, which is the equilibrium constant for reverse reaction, multiplies by concentration of C multiplies by concentration of D, which are actually the products. If we rearrange the above equation and we keep aside the concentration on one side and the equilibrium constants on the other side, we will get Kf by Kr is equals to concentration of C into concentration of D divided by concentration of A into concentration of B. And we all know that Kc is equals to Kf by Kr. So here we can put the Kc in the place of Kf by Kr, because Kc is known as equilibrium constant. So Kc can be represented as Kc is equals to concentration of C into concentration of D divided by concentration of A into concentration of B. Hence, law of mass action describes the relationship between active masses, reacting species, and the rate of the reaction. Okay, so moving ahead towards question number 8, which is derive the equilibrium constant expression for the synthesis of ammonia. Synthesis of ammonia from nitrogen and hydrogen. So in the question it is quite clear that ammonia is synthesized. It means ammonia is made from nitrogen and hydrogen. Okay, so here in the equation you can see that 1 mole of nitrogen and 3 mole of hydrogen combine together to give 2 moles of ammonia, and in return 2 moles of ammonia decomposes to give the reactants, which is nitrogen and hydrogen. So you can see that nitrogen reacts with hydrogen to give ammonia as shown in the following equation. This chemical equation shows that the reaction is reversible. According to the law of mass action, the rate of forward reaction, RF, is equals to Kf multiplied by concentration of nitrogen into the concentration of hydrogen power 3, because we have studied in the law of mass action that the number of moles comes into its respective power. So here you can see that there are 3 moles of hydrogen reacting here, so we will write 3 as a power of hydrogen according to the law of mass action. Similarly, the rate of reverse reaction is equals to RR, which is further equals to Kr multiplied by concentration of ammonia power 2, because in this equation you can see that there are 2 moles of ammonia being produced. And if we write the equilibrium constant for this type of reaction, we have studied that the products are written in the numerator, whereas the reactants are written in the denominator. So the product is ammonia, which is written as like this, and in the reactants are nitrogen and hydrogen, which are written in the denominator like this. These powers are actually the number of moles of the respective species. Okay, question number 9, write the equilibrium constant expression for the following reactions. There are 2 reactions given. The first one is hydrogen and iodine. They combine together to give hydrogen iodide. Then we have carbon monoxide, which combined with the hydrogen to give methane, CH4 gas, and water. Water gas means the steam is produced in these type of reactions. Okay, so for equation 1, you can see that the rate of forward reaction RF is equals to Kf, which is equals to the concentration of hydrogen and the concentration of iodine. Whereas the rate of reverse reaction is equals to RR, which is equals to Kr and the concentration of Hi power 2, because 2 moles of hydrogen iodide are being produced in this equation. The equilibrium constant expression, we know that products, Kc is equals to products by reactants. So by placing the values, we will get Kc is equals to concentration of hydrogen iodide divided by the concentration of hydrogen and iodine. Similarly, if we see for equation 2, the rate of forward reaction Rf is equals to Kf, which is equals to the concentration of carbon monoxide and hydrogen raised to power 3. 3 is the number of moles. Here in the chemical equation, you can see that 3 moles of hydrogen combined with 1 mole of carbon monoxide to give methane and water. Next is the rate of reverse reaction. Rr is equals to Kr, which is equals to concentration of methane and concentration of water. There are just 1 mole of methane and 1 mole of water are being produced. So if we write the equilibrium constant expression, it is just exactly the same we have write for the previous equation. Kc is equals to products by reactants, and the Kc will be equal to the concentration of methane and water divided by the concentration of carbon monoxide and hydrogen power 3. 3 is the number of moles of hydrogen. Okay, so moving ahead towards question number 10, which is how the direction of a reaction can be predicted. The direction of a reaction at a particular moment can be predicted by inserting the concentration of reactants and products at a particular amount in an equilibrium constant. This point has been studied in the last chapter, in the last topic of the chapter, which is the importance of equilibrium, where we have studied in detail then predict the direction of a reaction. So the Kc is equals to the molar concentration of product divided by the molar concentration of reactants. We can also compare the value of Qc with Kc so that we can predict the direction of the reaction. And we all okay, question number 11. How can you know that a reaction has achieved an equilibrium state? When the reaction does not stop, only the reaction of forward and reverse reaction becomes equal to each other but takes place in opposite direction. This is known as dynamic equilibrium. It means that the rate of forward reaction is equal to the rate of reverse reaction, right? So this is the basic explanation of dynamic equilibrium. We can further explain it that in a reversible reaction, dynamic equilibrium is established before the completion of reaction. At initial stage, the rate of forward reaction is very fast and reverse reaction is taking place at negligible rate. But forward reaction gradually slows down and the reverse reaction gradually gets faster. Eventually, both the reactions attain the same rate and hence achieve dynamic equilibrium. Okay. Question number 12, that what are the characteristics of the reactions that establish equilibrium state at once? The characteristics are: equilibrium always established in reversible reaction. Equilibrium never established in irreversible reaction. So the first point is quite clear that the equilibrium is always established in reversible reactions. And we know that in reversible reaction, the rate of forward reaction becomes equal to the rate of reverse reaction. These reactions never goes to completion. We will never ever get the final product in these type of reactions. These reactions can proceed in any way, like they can the equilibrium can be attained either from the product side or from the reactant side. Okay, the question number 13, that if the reaction quotient Qc of a reaction is more than Kc, what will be the direction of the reaction? If the value of Qc is more than Kc, the net reaction goes from right to left, or it will move in reverse direction to attain equilibrium. Okay, so we have actually studied the comparison of Qc and Kc in detail in the previous lectures. Last question of your textbook, that is, an industry was established based on a reversible reaction. It failed to achieve products on commercial level. Can you point out the basic reasons of its failure being a chemist? Okay, so the answer is the failure happens because the reaction is reversible and dynamic equilibrium is established between reactants and products. As products recombine to form reactants, so the desired commercial product for the required amount is not obtained. You will never get a proper yield of the product on the commercial scale because due to the reversible reactions, the products recombine to form the reactants. This is the general equation. A and B are the products which are combined together to form C and D, which are the reactants, and this is the reversible reaction, and this is in equilibrium state. It means that the products C and D will recombine to form the reactants A and B, and this reaction kept on for a long time and you will never get a desired product. So this is the basic reason for the failure of the industry to achieve products on the commercial level. So these are the 14 exercise short questions of your book. I hope everything is quite clear. You can ask anything in the comment section below.